Today we are looking at simple harmonic motion and damped oscillators, which are differential equations that describe swinging, bouncing, and vibrating systems. Undamped motion satisfies the equation y double prime plus omega squared times y equals 0, and this equation gives pure, unending oscillation. When we add resistance to the system, the equation becomes m times y double prime plus b times y prime plus k times y equals 0. This damped equation has three possible behaviors called damping regimes, and which one occurs depends on the sign of b squared minus 4 times m times k. Let us solve a specific example. We want y double prime plus 4 times y prime plus 4 times y equals 0, with the starting condition y of 0 equals 1, and the starting condition, the derivative of y at 0, equals 0. To solve this, we write down the characteristic equation, that is, r squared plus 4r plus 4 equals 0. Factoring this equation gives the quantity r plus 2 squared equals 0, so we get a repeated root, r equals negative 2. Because we have a repeated real root, this system is critically damped, meaning it returns to rest as quickly as possible without oscillating. For a repeated root, the general solution takes the form y equals open bracket c1 plus c2 times t close bracket times e to the power of negative 2t. Now we apply the first initial condition, plugging in t equals 0 and using y of 0 equals 1 gives us c1 equals 1. Next, we differentiate the solution to find y prime so that we can apply the second initial condition. Differentiating gives y prime equals c2 times e to the power of negative 2t minus 2 times the quantity c1 plus c2 times t times e to the power of negative 2t. Applying the second condition, the derivative of y at 0 equals 0, and substituting c1 equals 1 gives c2 minus 2 equals 0, so c2 equals 2. Putting these constants back into our general form, the final solution is y equals, open bracket, 1 plus 2t, close bracket, times e to the power of negative 2t. Now let us check this answer. We differentiate y twice and substitute both y prime and y double prime back into the original equation, y double prime plus 4y prime plus 4y, and confirm that everything cancels to give 0. Finally, we confirm both initial conditions at t equals 0, y equals 1 as required, and the derivative of y at 0 equals 0 as required, so our solution is correct.